Oh, hey there. Looks like you found your way to an educational video. We're talking about compound inequalities today. The essential question is, what techniques can I use to solve these compound inequalities? But I suppose before we get into techniques, we should talk about what compound inequalities actually are. So let's think about two scenarios. First of all, I mentioned this in class the other day. Sometimes highways, they have the speed limit that you can't go over, but then also to keep traffic moving, they have a minimum speed. So let's think about what some different legal speeds would be for this highway with a minimum speed of 45 and a speed limit of 80. Obviously, you could go 45. Obviously, you could go 80. And then you can kind of choose anywhere in between, right? You could go 50. You could go 62.3. So you can go any speed as long as it's between 45 and 80. So we need an inequality to represent the fact that our x, our values that work, live between 45 and 80. And we actually have represented this before in this class. You would do it like this. X has to be on the bigger side of 45. Also, x has to be on the smaller side of 80. So this is a compound inequality because x has to be bigger than this, but x also has to be smaller than this. And mathematicians like representing the in-between inequalities with two inequalities facing the same direction because it's very clean looking. So yeah, we'll practice more writing inequalities, but just know that's an in-between inequality. I thought of this other scenario. I think when I was in high school, I heard this. Let's say you're going 80 miles per hour on a highway. Obviously, if you go more than 80 miles per hour, so if you're going over the speed limit, at least if you're in America, there's going to be a cop car and he's going to like turn his lights on and come driving after you. But the theory goes that actually, if you're going like way, way, way faster than the speed limit, you might be able to go so fast that even if the cops see you going that fast, you'll like be able to get away from them because you'll be going so fast that they won't be able to catch up to you. So that's what this problem has to do with. It's an 80 mile per hour speed limit. So if you're looking at what speeds you could do and not get caught, obviously your speed could be less than or equal to 80 miles per hour, right? Because if you're going less than or equal to 80 miles per hour, the cops are not going to catch you because you're driving legally. So this is, yeah, the legal speeds that you could drive. But also what we're saying here is probably you could get away with going so fast that the cops wouldn't be able to catch up to you. And for this problem, they're saying, hey, probably if you're going faster than 120 miles per hour, the police officers won't be able to catch you. So if you don't want to get caught, either you have to go the speed limit, go less than or equal to 80, or also you could choose to go so fast that the cops wouldn't be able to catch you. So greater than or equal to 180. And that would represent illegal speeds, but illegal speeds that are so fast that the cops might not be able to catch you. So these are both good speeds to go. This is another type of compound inequality. It's kind of the opposite of in between. Instead of in between speeds working, here in between speeds are the speeds that would get you caught. So like 90 miles per hour, 100 miles per hour, those speeds aren't going to work. But anything to the outside, like if I go 45 or 50, that's legal. If I go 125, that's super fast, so the cops wouldn't be able to catch me. So this is another type of compound inequality, looking more to the outside. Anyway, let's see how these things are represented and how we would solve them. First of all, we're going to start with one of the or inequalities. So this is like this example. Yeah, I have two different inequalities and I'm saying either this one works or this one works. As long as x is in one of these ranges, I'm good to go. These are easy to solve. All you have to do is solve the two equations separately of each other. So you just need to solve separately. We're just going to put the results on the same graph. So solve separately and then we'll graph on the same one. So here's what you do. Subtract 3 from both sides, so 2x less than 6. Divide through by 2, so x less than 3. Okay, great. So that's the solution for the 1. Over in this one, you're going to add 6 to both sides, so 3x greater than 18. Divide through by 3, so x is greater than 6. So here's my answer. Here's my compound answer. Either x has to be less than 3 or x has to be greater than 6. And I'm going to graph these on just one graph. We'll see which values are legal. So put your 0. Here we kind of have two critical values. We have 3 and 6. So what they're saying is that x could be less than 3. That's represented by this arrow. Or x could be bigger than 6, and that would be represented by this arrow. So as long as you have a value in this arrow or a value in this arrow, that is a value of x that will work. The only values of x that don't work are like 4, 5, 5.5, things in between 3 and 6. Those are the only ones that don't work. So ORs are easy. Just solve separately, graph on the same number line. What's a little bit trickier to solve is the in-betweeners. So here we clearly see that they're going for something, x is going to live in between two values, and there's a technique. I need to do this. I need to get x by itself. I'm trying to isolate x, but I can't really isolate it over here or over here. That would be weird. I need to specifically isolate x in the middle. So what I would recommend doing is maybe with your finger, cover up this side, cover up this side, because really I have 3 sides to my equation now. Only focus on the middle and figure out what's going to isolate x in the middle. So in this case, well, clearly I need to subtract 4. That'll cancel it. And then I'll divide by 2 in the second step. If I subtract 4 from the middle, I need to keep my equation balanced. So shouldn't I subtract 4 from here also? But wait, there's also a third side. So also I need to subtract 4 from here. So here's what makes the in-betweeners tricky. There's kind of 3 sides to the equation now. 1, 2, 3. Whatever I do to the middle, I also need to do to both outsides. So I'm subtracting 4, that leaves me with 6, less than or equal to 2x, less than or equal to 20. Now, I'm still trying to isolate x in the middle. So again, if you get confused about either of these sides, just cover them up with your fingers. To isolate x in the middle, I need to divide by 2. But if I divide by 2 there, I also need to divide by 2 here and here to keep all 3 sides balanced. So now I've reached my goal. I have just x in the middle. On the right-hand side, I have 10. On the left-hand side, I have 3. This is my final answer. Look, x is isolated in the middle, and I have a number on either side. Now, to graph this, we know that this is going to need to be in between. So my graph should reflect the fact that x is living between the values of 3 and 10. Look, x has to be bigger than 3, but x has to be smaller than 10. X has to be in between 3 and 10. So let's make our number line. Here's 0, here's 3, 10 would be more down here. And I need closed dots because I have less than or equal to and less than or equal to. And again, x has to be between those two. So I'm just going to draw that line. Or if you feel like shading it on the graph, you could do something like this. So there actually is no arrow in this case. I'm literally just shading in between 3 and 10 because values that are between 3 and 10 are the ones that work. Let's try one more example of the in-betweeners because they're a little bit tricky. Remember, our strategy is we need to isolate x in the middle. So I would cover up either side. Just look at the middle. Let's see, to isolate x, I'm going to need to add 3. So since I add 3 here to cancel, I also need to add 3 to both of the outsides. So on the left, I have -2. Now I just have -x left in the middle, and on the right, I have 5. Cool. Again, if I'm trying to isolate x in the middle, I need to cancel that negative. Remember, it's kind of like -1. So let's divide by -1. Now don't forget, when I divide by -1, not only do I need to do the division, so 2, x and -5, but I also need to change the direction of the inequality. So greater than, so this less than becomes greater than, this less than also becomes greater than, and here's my final answer. And remember, I changed the direction because I was dividing by a negative. Now, again, I have an in-betweener. It's saying that x, it needs to be smaller than 2, but it needs to be bigger than -5. So let's make my graph. Now don't make this mistake. Don't put the 2 down here and the -5 up here. I know that's how they look in the problem, but remember, this is a number line. -5 should be the lowest value. 2 is going to be the highest value. 0 goes in between those two values, maybe about there. And again, x needs to live in between the two values. So I have -5, I have 2. I'm using closed dots because I have equality. And I'm going to be shading in between these two values. Great, so I'm done. Just a summary, when solving or graphing an OR, so this was like example 1. Remember, you're just going to solve separately, and you'll kind of get two separate equations, but you're going to make one graph, just one graph. So remember, example 1, I solved this one, then I solved this one, but I put the two arrows on one graph. With an in-betweener, so that was like example 2 and example 3, you're going to isolate x in the middle. Isolate x in the middle. And whatever you do to isolate x in the middle, you have to do to both outsides. So here, if I decided to add 3 to isolate x, I also need to add 3 to this side and this side. And then remember, your graph should look something like this. You're shading in between because it's an in-betweener. So these things aren't too complicated, but they are going to require a little bit of practice because the techniques, yeah, they're just a bit weird, especially for the in-betweeners. But hopefully that video is a good introduction to how to solve these. We'll practice more in class. Thanks.